Hey guys, welcome back. So in the last video, we looked at hash indexes, right? We looked at how great it was, how do you store data on the file, how do you create your indexes, what benefits it gives, and so on. There was one very big drawback of hash index. That was all the keys of the hash index need to fit into memory, right? Now that's a pretty big limitation. Okay. So today we're gonna see something called an LSM tree and an SS table, which is gonna help us overcome this limitation. By the way, this is used at pretty much all big NoSQL databases like Cassandra, HBase, 11DB, so on, right? So, this is going to be very important for your system design interviews and for your general, learning of these NoSQL databases as well. So, stay tuned. So, earlier we saw, we have a file and we used to keep appending entries to the file, right? For now, let's just assume that somehow the file has entries that are sorted, okay? Of course, how that gets sorted is something we look at soon, okay? In the last video when we discussed hash index, we discussed that we would just keep writing new entries to the file, right? Of course, that is not necessary to keep it sorted. But just for now, let's assume that this file is somehow sorted, okay? And let's see what benefits the sorting gives us, okay? And once we see that, let's see how we can sort in a pretty efficient manner, okay? So let's assume for now in each file, the entries are sorted, okay? So this is actually what is called an SS table or sorted string table. So now when this is sorted, let's see what advantages we get along with it. Now, the biggest advantage that we get is that we don't need our index to map every key with its address. I'll tell you how. In hash index, what we had for each and every key that we had to map. For this key, this was the file and this was the address, right? Or the byte offset. When the data is sorted, you don't need that, okay? What you can do is, you can have something called a sparse index, okay? What do we mean by sparse index? For example, if you see here, there's handbag, handcuffs, handful, handicap, and some number, right? Where the keys are strings and the values are numbers, right? Some count maybe, okay? So here, if you look at our index, we have an entry for handbag and then we have an entry for handsome, but we don't have an entry for any of these particular key values, okay? Now, what benefit that it gives us, okay? Let's say we want to search for, maybe handicap or handiwork, okay? Or let's say handkerchief. What you can do is you can look at this index and you can say, okay, if my handiwork is supposed to be present, it would be in between handbag and handsome, right? Because they're all sorted. So when they're sorted, for example, if you have a sorted number of 1 to 10, and if you know where 1 was and where 10 was, if you're asked where is 5 present, you would know that, okay, 5 is supposed to be in between 1 and 10, and I'll just look in between 1 and 10, right? So you essentially kind of look at an index and find two keys in between which your key would be present, right? Of course, there won't be a lot of entries here. So finding the range would be pretty easy. And once you find that range, you can just do a linear scan. And that's going to be very small set compared to your entire data, right? So scanning between handbag and handsome is fine, correct? So this is what is sparse index. Essentially, you don't have an index for every key. You have one for a couple bytes. Let's say in general, what happens is there's one key per 4 KB, which, is pretty good in terms of performance. Okay. So this is sparse indexing. So this itself is a big relief from our hash index, where in hash index, you needed to have an index for each and every key. We couldn't do the sparse index there because in hash index, the files were not sorted, okay? Now, since the file is sorted, that is the only reason why you're able to do this, okay? If the files were not sorted, you would not be able to do this, right? So that's sparse index, okay? This is the first advantage of having the file sorted. Again, we'll look at how to sort that file a little bit down the line, but this is one of the biggest advantages of having each file sorted, right? Second, merging and compaction becomes easier, right? If you don't know what I'm talking about, go watch the previous video first. We've discussed what merging is, what compaction is, how are data stored in the file, all of those really good in-depth concepts in the previous video. I link it here. Okay, go watch that and come back here. Okay, so now merging and compaction becomes really easy. Why is that so? Okay, let me again come to an example. Right now we have these three files, and what we need to do, as we saw in the previous video, there's a lot of wastage space here. See, there's handful here, handful here, handful here, right? There's handicap here, handicap maybe somewhere here. There's a lot of wastage space, right? A lot of duplicate key values because our updates are not updating data in place, right? It's adding a new entry to our file, which has its own advantages, but now that has wastage space. So that's why we do merging and compaction. When it's sorted, what you can do is now you can run a merge sort algorithm, right? You just compare the first two, you see, okay, handbag is smaller than handcuff, so you put handbag in the merged file. Then you compare handful and handcuff, you see that, oh, handful is the smaller, so I will put handful on the merged file, right? Now running merge sort is pretty easy, right? We all know how merge sort works, correct? And this type of merging only works if your file is sorted, right? So, the compaction and merging process becomes easier and faster, right? This is the second advantage of having each file in a sorted order, correct? Third, earlier we used to have an index for every key, right? But now since we have it only for a handful of keys, let me come back up here, okay? And let me move this. Okay. Now what you can do is, since you're only, let's say for this entire block, you have one index, right? You don't need this to be stored as it is. You can actually compress this particular block, which actually reduces the size on disk and it reduces the IO bandwidth. It's not only about the number of IO operations, it's also about the bandwidth, right? During each IO operation, how much you're reading and writing, right? And this also reduces your IO bandwidth, okay? So you can also now compress your blocks since you're only having one index for a handful of keys, correct? And those handful of keys can be now compressed and stored on disk. Because either way, when you're reading, you have to read it the whole block. Your disk actually stores data in blocks, right? So even if you're reading a single line from a file, the entire block is loaded, right? So might as well, compress that entire block, correct? So now we've actually seen the benefits of keeping the file sorted, right? You don't need as much memory as the hash index because you're not indexing each and every key, correct? And you get pretty good compaction and merging algorithms, and you can compress data, right? And so these are the three benefits. Now we know that having a sorted file is gonna give us good benefits, but now the problem is earlier in hash index, if you remember, we were appending new entries onto the file, right? But now if you have to sort it, running sort on each insert is going to give you O of n log n complexity, right? Because you have to sort the whole file during every insert. Now that's bad. How can we improve it? That's where we use trees, okay? If you remember, even a simple binary search tree, once you have a balanced binary search tree, now you can read the tree in order and then get a sorted list, correct? So now we're going to use that property of trees. We're going to use a self-balancing tree, something like an AV or a red-black tree, right? To make this more clear, let us go through an insert flow, okay? Let's say whenever a new insert is coming in, you maintain a tree, okay? An AVL tree or a red-black tree, okay? You maintain a tree. What you do is, when this tree reaches a certain threshold, that is when you actually read it in sorted order and write it into a file, right? Now this read is not, when you read it, you can actually get it in sorted order, right? So it's not going to be n log n, it's going to be O of n. And not even O of n, O of k, the number of entries in the tree only, correct? So, and that's a one-time operation. Like, let's say your threshold for the tree is 4 KB, okay? So once every 4 KB, you're actually reading the entire thing and flushing it on disk, right? Which is fine. So this way you get your files in sorted order, and you also get pretty good insert or write operations because you are writing in memory. You are not writing on disk. Okay. Log compaction and merging can be done asynchronously in the background, right? Compaction and merging is something that we have discussed already. Okay. it can be done asynchronously as usual. Okay. Of course, I can hear your mind voice from here. You're saying, what if the machine crashes in between? All the data is going to be lost, right? Again, that's where append only log or write ahead log comes in, right? You write once to the in-memory tree and once to your write ahead log, which is pretty fast, right? You're still appending only. That doesn't have to be sorted. Its only purpose is for crash recovery, right? So that way we're safe from machine crashes and you still get pretty good writes. Okay, let's go through a read flow. In the read flow, first you search for the key in the LSM tree. Okay, the term LSM might be a little confusing because we just said avian trees. The term LSM stands for log structured merge trees. Okay, it was made. I mean, when this first idea was proposed, people named it this. I'm not really sure why they named it, and it just kept continuing on. Okay, so LSM trees for historical purposes. Okay. So what you do is when you get a read, you go to the tree, you go to the in-memory tree, and then you try to see the keys present. If it's not present, now you have multiple files, right? The index is maintained for each file. You don't have to have a global index. You can have a smaller index for each file. What you can do is now you go check the index of the latest segment or file. If it's not present there, you go to the second latest, third latest, fourth latest, and so on. Okay? This is how read works. Of course, here we are prioritizing writes more than reads. Okay. Remember, guys, there is no such thing as imperfect system, right? If you're optimizing for reads, you're gonna get a little slower writes. If you're optimizing for writes, you're gonna get a little slower reads, right? That's how things work. Okay. So although this reads are a little slower than before, it's not as slow, but your write performance is gonna be massive, right? Cassandra. You've seen how Cassandra works and the kind of insane write performance that it gives you, right? It's because of this method. It uses this particular method to do its writes. Okay, now what are the disadvantages, right? Of course, I just said everything has its advantages and disadvantages, right? This is not a perfect system. So what are its disadvantages? The in-memory tree is lost if computer crashes. We just discussed it, right? You use append only log or write ahead log, however you want to call it, right? They're the same thing. You write once to the tree and you write once to the file, right? The write ahead log, and this doesn't have to be sorted, right? The only purpose of this file is for crash recovery. So this doesn't have to be sorted. You can just keep adding entries below one another. Once this flush is successful, you can remove this particular file. There's no need for it because it's persisted. One other disadvantage which we just discussed was the reads are a little slower, okay? Because now what you have to do is you have to first check your tree. If it's not present, you check the latest file. If it's not present in the latest file, you check in the second latest file, the third latest file, the fourth latest file, and so on, right? To optimize for keys which were never written, okay, databases use something called a Bloom filter. Of course, I'm not going in depth about Bloom filters because that is going to be its own episode, so to speak. It's a pretty neat trick on how it detects whether a key was inserted or not inserted ever, right? It's a pretty neat trick. So we're going to be looking at that in depth in a separate video, okay? Just know that for now, there is something called a Bloom filter which is supposed to ease this a bit. But again, reads are a little slower here. Not very slow, but slower than hash indexes. Okay. Again, as I said, this is used in Cassandra, HBase. Google Bigtable is actually the one which kind of introduced this concept of LSM trees and SS tables. Google did a lot of crazy work earlier, guys. We're going to be looking at a lot of that work as we go on, okay? Inserts are now super fast since writes only go to the in-memory hash map and the write ahead log, right? Which is pretty fast, okay? Both of those are pretty fast, okay? Performance optimization. Yeah. So what if the key is not present in the DB, right? If the key is not present, ideally, again, as I said, right, we're going to use something called Bloom filters. If that's not there, we would be searching every segment. Let's say there's 10,000 files. Right now, you will actually go look at 10,000 files before you actually realizing that this key was never inserted, right? So that's where Bloom filters come into picture. It's something that we'll look at in a couple of videos very soon, okay? But on a high level, Bloom filter essentially, given a key, tells if the key exists in the DB or not, right? Of course, that's also not perfect, and there's a gross simplification of what Bloom filters actually do. This is the index that's and the storage model that's used in most NoSQL tables, right? Cassandra being one of the most popular for has having massive amount of writes, right? So to reiterate, we have a in-memory tree. Okay, whenever we get a insert, we write it into the tree. Okay, this is an AV or a red-black tree, essentially a balanced tree where we can read what we've inserted in a sorted order, right? So once this tree reaches a certain size, we flush it onto a disk. Now this file is gonna be sorted, and this gives us, benefits like we create something called a sparsed index, as we saw, right? This sparsed index helps us not keep an index entry for each and every key. Instead, what we have to do is we just have one index entry for a couple keys, right? So this reduces the dependency on memory quite a bit, right? And your keys don't have to fit in memory, right? That's the biggest benefit that you get with this. Of course, with pretty really good write performance, right? So that's it for this video, guys. I hope you like this, and I'll see you guys in the next one. Bye bye.